Hi guys, this is Neel from InCore Semiconductors. I'm going to be talking about Riscof, which is a probable candidate for the next generation compliance framework for Risc-V. I'm going to start the talk with defining what ISA compliance is in this particular context. I'm going to then introduce Riscof and what are the promises on which Riscof is built. I'm then going to go over some of the components of Riscof like RISCV-CONFIG, the CGF, the ISAC, and the CTG. I'm going to conclude with how Riscof assembles all of these individual tools into a complete single utility for compliance. So, to start off, what is compliance? It means that an implementation of the ISA meets all requirements under all conditions as specified by the spec. And if you extend that, a fully compliant device would basically mean a bug-free implementation. Now, we all know RISC-V is microarchitecture agnostic. It does not mandate how a particular extension is implemented. And more importantly, it gives you extreme configurability in choosing what sort of extensions you really want to implement. So this is almost impossible to create an exhaustive test suite for all implementations. But what is possible is to build small test suites focused on to check compliance on limited and focused areas of the ISA. So what we're trying to say now is that compliance is a very small subset of design verification, which means that if you call yourself RISC-V compliant, it does not mean that your implementation is bug-free or that your implementation works exactly well as any other RISC-V compliant core. All it means is you've been capable and successful in actually passing the compliance test, and you can now use some of the brownies from the RISC-V Foundation, like the trademark or the logo, or as the deem fit, what it means to be RISC-V compliant. So the goal of Riscof was quite simple and basic. We had open instruction sets, we had open formal models, the open GNU toolchains, software stacks available. We thought, why not have an open source compliance framework as well? And we needed to satisfy 4 different criteria. We said it has to reduce dependence on external tools. You don't want to have locked down to third-party closed source tools or licenses. We want to be device agnostic. A RISC-V implementation could include anything from an ISS to cycle accurate models to architectural models or actual soft cores on FPGAs or RTLs, right? We should be able to cater and integrate all of them and perform compliance for each of those devices. The compliance framework has to be scalable for future ISA extensions, whether it's extracting coverage or running tests or the size of the test that comes up with different extensions. The framework has to be capable of expanding and extending to accommodate those extensions. And more importantly, we wanted a single utility which can satisfy the needs of all compliance requirements, whether it's maintaining the database or maintaining the test suites themselves or extracting coverage. All of this should be available in a single utility. You should not be jumping around different applications to achieve compliance. So to start off with, the first and most important configuration component of Riscof was the RISCV-CONFIG, which basically caters to the need of having a simple and a simple standard format to define the different choices that a vendor makes while implementing a RISC-V device, right? So as you know, RISC-V already gives you a lot of options, and what RISCV-CONFIG does is gives you a YAML format which allows you to define and express those choices that you've made. As I said earlier, you need to be able to integrate different devices, and that's possible by defining API plugins for different models. And Riscof has basically done that. It has kept itself away from any specific models or any specific form of RISC-V implementations and allows you to integrate anything ranging from instruction set simulators all the way to silicon. CGF is a cover group format which allows you to define different cover points and specific coverage groups, which can help you define what parts of the ISA are required to be satisfied by the tests. What's the quality of the test? That's the metric that we're going to be using through CGF. ISAC is the tool which allows you to extract coverage based on what is defined in the CGF and what the execution of a particular test looks like. And once we had defined through CGF and through different cover points as to what should be included in the test, we've gone a step ahead and defined CTG, which is the compliance test generator, to actually generate those tests and implement those tests in an automated fashion rather than write them from hand. So RISCV-CONFIG, the primary purpose is to capture a valid and legal specs of a RISC-V device and filter out illegal configurations early in the stage. You do not want to take an illegal configuration device into the RISC-V framework, into the Riscof framework, and have 10 or 20 different tests failing to figure out that you've made a wrong choice in the implementation. So RISCV-CONFIG is basically a YAML specification which is split into 2 specs as of today. That's the ISA spec and the platform spec. The ISA YAML basically captures all the different hooks and the choices that the unprivileged and the privileged ISA specs talk about. The platform spec is more related to the SoC or the InCore or the non-ISA specific parts about the implementation, like memory maps, reset vectors, number of NMIs that you have. Now the split between specs is scalable. You can now have multiple different types of input specs like debug, trace, CLI, as and when they get ratified. You could start adding those as separate specifications which get validated through Risc-V-CONFIG. The ISA spec as of today also has the ability to define the WARL, the WLRL specifications of RISC-V CSRs. The most important aspect of Risc-V-CONFIG is the CDPRIS package which we use for validating the particular input specs. So the CDPRIS package allows you to define a schema or a set of rules for the YAML input which needs to be satisfied. If not, Risc-V-CONFIG is going to give you it's going to throw back an error indicating what particular legal configurations you've actually chosen. This could mean something like implementing a D extension without the F and not having the ZICSR when you've implemented either the F or the D, right? So all of these combinations are validated, and Risc-V-CONFIG gives you feedback whether the choices of the ISA that you've made are actually legal or illegal. You can also define custom validations across nodes, so you can define Python functions which can perform much more complex operations on different inputs that are present in the YAML and validate whether they are coherent and a legal specification. The normalization and trim are pretty straightforward. The input spec does not require to have all the nodes specified. The vendor need not specify everything that the ISA talks about. So the Risc-V configures it and assigns default values to all of those inputs. And what happens as an artifact of that is everything that comes out of Risc-V-config looks exactly alike except for the value. So you have 100 different hooks possible in the ISA spec. Those 100 nodes are going to be available in all checked YAMLs, and every implementation is only going to differ in the values of those 100 nodes. Right? The trimming function is sort of optional here. It allows you to strip away certain fields that you don't require to be that you don't want available in the checked YAMLs. This work is completely open source. It's available as a Python package in PyPy, and you can find more details about this in the link at the bottom. CGF is the acronym for coverage group formats. It's a simple to use and human readable YAML format to define cover groups or cover points. Basically has two categories of informations. There is a data sets that are declared at the top. And these data sets can basically define different operand addresses for a single instruction. These are data sets that can be used across instructions, so they're defined independent of any particular one instruction. As you can see at the bottom of the screen, you have an operand combination where you say that you would like to see RS1 and RS2 to be equal, which means they're both the same registers, but they're not the same as the destination. And you could go and define much more different combinations, like all the registers, all the operands and the destinations being the same registers, or all of them being different. You could go a step ahead and define the combinations of the values that you want to see at the operands. For example, you want to see both the operands being positive, negative, a mix of those. You can define values like int max, int min, -1, alternating ones, zeros, and any specific values of interest as well. We've also been able to support custom abstracted functions like walking ones or walking zeros, which typically would unroll to 32 or 64 individual cover points, but by defining them as abstract functions, this becomes a single line definition, which obviously has to be elaborated and expanded by the extraction tool itself. The second category of information that the CGF holds is the cover groups themselves. For example, in the example that you're seeing now on the screen is the add coverage, which is basically the name of the label. The config node basically tells you under what conditions of choices that the implementations should this particular label be in effect in the report. Basically, if only for those implementations who have implemented the I extension should this coverage label make any sense to them. The opcode basically talks about the instruction for which the cover points following this is relevant for. What you're seeing next is for RS1, RS2, and RD that you want to make sure that you've seen enough add instructions where all the operands and destinations have seen all 32 registers. The opcom basically points to the R format operand combinations that you're seeing on the left bottom corner. The value combinations are now a list of different data sets that have been defined. You have different specific data sets for RS1, RS2, a combination of RS1 and RS2. You also have RS1 walking ones and walking twos, walking zeros for RS2. So using this anchors and aliases, we are able to keep the small size down. So we are reusing a lot of these data sets, declaring them at one point and reusing them for multiple different instructions. Today, for 37 instructions, we are able to define more than 6,000 cover points using the CGF in less than 1,000 lines of code. We believe this format is scalable, and it will be can accommodate for the future extensions that Risc-V is already working on. So the CGF format itself is available, and within Riscof, a draft of which is open sourced. So ISAC is the tool which will help you extract coverage. It's a derivative of an open source tool called Rita, which was developed by our team previously. The primary purpose is to collect coverage of the cover points specified in the CGF for an execution trace. So each time you run a test on one of these simulators like Spike or Sail, they have the capabilities to generate an instruction trace or an instruction log, where for every instruction you're capturing is the privilege mode, the instruction address, the instruction encoding, and any architectural state that has been updated. What ISAC does is it captures this instruction meta and parses through the CGF and says that is there any cover point which is of interest to this particular instruction? If so, increment the cover point by 1, right? So it's as simple as that. The parsers today are independently built, so you can have multiple different parsers for different types of instruction logs. For today, we support Spike and Sail. You can create your own parsers and plug them into ISAC. The backend, which is basically taking up the CGF and extracting coverage, is completely independent, so you do not have to worry about the changes that the parsers undergo. To be more conservative in the way we extract coverage, we've added the ability to actually define specific regions of interest in a particular trace. For example, when you're actually running a test from compliance, it's going to have a lot of other pseudocode, a lot of other code. For example, the epilogues or the prologues, which include boot codes or halt conditions from the vendor itself. Those instructions in those places need not contribute to the coverage, and you can specify that to ISAC by defining specific addresses of region of interest. And ISAC would only look at coverage, updating the coverage only for those instructions. Going a step further, what we also do is we specify specific coverage labels that need to be updated for a particular instruction trace. So when you're running the add test, you only update the add coverage label and not the load store coverage labels. And this allows you to define exactly how much a particular test is contributing to coverage as well. So ISAC at the end of execution gives you a YAML and an HTML report for each instruction log. It also has the ability to merge multiple different YAML reports and give you a single HTML report for which will now identify as the coverage for an entire suite of tests. So this too will be made open source soon. We are working on the final kinks to make sure it's stable enough. So having defined what parts of the ISA we would like to actually cover as part of the CGF, we believed instead of writing tests by hand for each of those cover points, can't we treat them as constraints and put them against a solver which can now generate instructions for each of those. So that was the genesis of CTG. The idea is to build an automated test generator to maximize coverage using minimal number of instructions, and it's completely written in Python. The CGF cover points that you saw in the previous slides is what is presented as constraints to the CTG. We use a Python constraint solver to basically find solutions for each of those cover points. The CTG basically has a predefined data set for specific for different types of instructions. Now the problem with Python, with constraint solvers is if the data set is too huge, it's going to take a lot of time to converge and you're going to end up in combinatorial explosion. So to avoid that, we've defined specific data sets of values of interest like walking ones, alternating ones and zeros, max, min, specific values for specific instructions which are of interest and not everything. Not all possible values. Again, remember we are trying to perform compliance and not design verification. So this particular assumption works well in that context. We've also gone ahead and figured out that different types of instructions or formats of instructions like the R type, the B type, and the S type that the ISA spec actually defines will require different types of algorithms to actually solve those constraints. And we've basically created plugins so that for every different type of format that the ISA specifies, you can create a dedicated algorithm for those bunch of instructions. The CTG also maintains a database of attributes of instructions. So for every instruction, it's going to capture what format does it belong to, what are the data sets of interest for RS1, RS2, or if it's an immediate field, what are those values that should be used. It also has a set of assembly macros which are used. So the CTG does not spit out raw assembly instructions. What it does is it uses macros which are specified in the instruction attributes. So using this methodology, we are now able to generate 35 tests in less than 3.5 minutes for the RV32I base extension. These are all sequential runs. We also have the ability to generate randomized solutions which take around 15 seconds because that speeds up the constraint solver. However, this is not stable, and what I mean by that is though you will always get 100% coverage for every instance of the CTG that's run on randomized arguments, the signatures generated by those tests are going to be significantly different on each run, but they would still meet your coverage requirements. So this tool will be made open source, and obviously the tests generated by the CTG are, they do adhere to the compliance test format spec. So the test format requirements for Riscof, there are a lot of other macros, but I'm specifically going to talk about two important macros that the Riscof really depends upon. The first macro is the RV test ISA. Basically, every test that has to become part of Riscof needs to have this test which indicates what are the environments under which, or what is the machine mode, what are the MARC, the architecture under which this particular test is supposed to be compiled against, right? So a typical use case of this would be to generate the MARC and the MAVI arguments for the GCC compiler. The second macro is the RV test case macro, which is again an empty macro which has no architectural state update. But the string over there is of huge concern, which actually identifies what this particular test or what this part of the test, when this part of the test is going to be enabled, under what conditions of implementation choices should this test actually be enabled or should be run on the particular duty. So if you look at the bottom, the two strings, the first one being check ISA followed by a regular expression, what that means is this test or this part of the test should only be enabled when the implementation has I and the ZISR extensions enabled. Or if you look at the second string, that particular test is to be enabled only if it has, if the implementation has hardware misaligned support. Moving forward, one important condition is every test that enters into Riscof should be able to generate a signature in the memory section, and the signature basically captures the essence of the test. For example, the add instruction, the signature, for example, the add test case, the signature would typically hold the outputs of these operands, operations of the add instruction itself. Now what Riscof does is it takes the add test, runs it on the DUT, generates a signature, runs the same test on the reference model, generates a signature. Remember, the reference model is now trying to mimic the DUT as much as possible, which means if these signatures matches, you now have successfully passed the compliance test. So this is the entire framework for Riscof. It basically covers almost all the tools that we've discussed. So you start with the DUT YAML, which is your implementation choices that you made for your DUT. You pass it to RISCV-CONFIG and you get a standard YAML, which now serves multiple purposes. One of the purposes is to actually configure the golden model in order to mimic your DUT. The other usage of the standard YAML is actually to select tests from the directory, from the test directory, a specific list of tests which are to be run on the DUT and the reference plugin. Once the list of selected tests is available, Riscof runs these, simulates these tests on top of the DUT and the reference models, generates the signatures, compares them, and generates an HTML report, and which gives you an indication of how many tests have been passed and failed. Simultaneously, Riscof will also extract the execution trace for each test from the reference model, pass it to ISAC, and give you a coverage report for the configuration that you've chosen. So in the previous slide, we've talked about the test directory, and the test directory consists of tests that are generated by CTG and also some other tests which are written by hand for certain specific scenarios. Riscof also has an internal utility called dbgen, or the database generator, which basically generates a database YAML, which captures the different attributes of each test. For example, what's the file name, what's the commit ID, which is the last commit ID that changed that particular test, what are the ISA requirements, how many parts that particular test has, and for each part it defines what are the conditions under which that particular part can be enabled, and if enabled, what are the macros that need to get enabled. Combine this test list database YAML with the standard YAML that comes out of Riscv-CONFIG, you will now have a test selector utility in Riscof, which is now able to identify which of these tests, out of these thousands of tests which are available in the test directory, which of these tests need to actually be running on the DUT and the reference model. And that basically comes out as another database in a YAML format, which captures the working directory and the macros of the ISA string, which is required for compiling and executing those tests. We've been talking about API plugins, which allows you to do this, and Riscof basically gives the reference or the DUT model, basically a standard API plugin which allows the vendor to define how to build its own model, how to configure the model, how to simulate the model. So the vendor has complete control over the choice of SDK, its own environment, whether it wants to do RTL simulations in Model Sim or very later, or you want to perform something on ISS simulators like Spike or Sail. You can choose whether you want to make file based generation, you want to run the entire test suite in parallel or sequential, you want to have more debugging capabilities. All of that is available through the plugins. And we've given a lot of examples of these, which are available in the link presented below. So far we've been looking at Riscof from the compliance perspective and what we've done so far, but you can actually start extending it to be much more than compliance. The first step would probably be to define much more detailed cover points and cover points of interest, which can take a step towards verification and get out of the small circle of compliance. The other idea is to enhance ISAC to now start covering or profiling the trace for more specific inputs like branch histograms, PC histograms, and other things like that. You could also use Riscof to run on custom suites. So if you have your own test generators or if you have your own random test generators, as long as they meet the test format spec, Riscof should be able to execute those for any reference and DUT models. So the takeaway from this talk would be the idea is to build all requirements under a single utility called Riscof for compliance. It's easy to install. All of these packages that you've seen so far are available as PyPy packages, and it's a single command to install all of them. It's a scalable solution which can meet all the current and future extensions and requirements of the ISA. All packages are available under permissive open source licenses, and more importantly, the framework does not require high skill sets or specific expertise. It's just Python, YAML, and assembly, which are pretty easy to acquire skills and will help people to contribute more aggressively. These are the list of contributors. Pawan, myself, Shivani, and Lavanya have been contributing to these projects. Special acknowledgements to Alan and Simon for their constant support and feedback on the development of these tools. Thank you. Have a nice day.